Well, hello, welcome again to our journey into number theory, and we're going to move on now and start having a look at the averages of arithmetic functions. So, as mentioned earlier, the values of the arithmetic functions behave very erratically. For example, the function tor of n, which counts the number of factors of n, number of divisors of n, takes the value 2 infinitely often whenever n is a prime. So, for example, if we look at this graph here, there's a graph of tor of n, and you can see that it's all over the place. There's the value 2, it's taking this infinitely often. I've only done up to 80, but you can see the things are all over the place. And so it's hard to make much sense of that. And similarly, sigma of n, if we look at sigma of n, the sum of the divisors of n, we find the same thing happens. We're going to get similar sort of very strange behaviour. And what we'd like is to try and smooth out the data in some way and see what it looks like. And I'll show you the pictures of that a bit later. But that's what happens when you just look at these two functions, tor and sigma. So how do we smooth out the data? Well, we look at the average rate of growth, and we can look at the average rate of growth by simply studying this function of any arithmetic function by studying this particular sum here. So we take the sum of our function f of k from k equals 1 to n, and we divide by n, which just gives me an average. Now, we study this by looking at sums of this shape, that is, sums of the form k less or equal to x, fk, where x now I want to be any positive real number, and it's understood in this context that this k then varies from 1 up to the floor of x, because k is supposed to be an integer. And so when I write this sum, it's an abbreviation for the sum k equals 1 to the floor of x. Now, to describe the growth rate of these functions, we're going to introduce what's a standard notation, capital O or big O of f of x, also known as Landau's notation. Now, you may in some other courses have seen little o of x, which we will look at a bit, we might use a bit later, but in all the material we're going to do at the moment, we're just looking at big O of x, which I'll define down here. So it says that suppose g of x is positive, eventually for all sufficiently large x this function is positive, and that we can find a constant so that the absolute value of f of x, just in case it goes negative, over this g of x is less than m for all sufficiently large x, that is for x bigger than some value a, for all x bigger than that. In that case, we write f of x is big O g of x. And we can read this as f is of order g. Sometimes I'm going to say f is big O of g. Now, the big O notation, what this is going to enable me to do, I like to think of this as sweeping the dust under the carpet. You get rid of stuff that you don't want to see by using this big O notation. You can in some sense mathematically sweep it under the carpet because it's just confusing matters, and it enables me then to concentrate on the things that are important, not the things that are unimportant. Also, just another notation, we say that f is asymptotic to g and write f twiddles g means that the limit of the ratio of f and g is 1. So just a couple of examples of playing with this notation, just to get used to the notation. So just a couple of simple examples. I'm going to start off with just a quadratic. So when I write something like f of x is x squared plus 2x plus 3, if I'm thinking about dominant terms, if I'm thinking if x is large, where's the money? Well, the money's here. And we're going to call this is going to be big O of x squared. So in some sense, if x is large, that's the most important term, and I want to sweep these two terms under the carpet, which I do by using the big O notation. Now, why is it big O x squared? Because if you divide these two, then you can say, look, if x is bigger than 3, then 2x plus 3 is just going to be less than, these terms are going to be less than x squared, and so this is less than 6x squared on x squared, which is 6, provided x is bigger than 3. And that means that this is big O x squared. If we take something like the log of n factorial, what's that big O of? Well, log of n factorial is just this, and we can say this is n is less than, n equals n minus 1 is less than n minus 2 is less than n, so this is less than log of n to the n. I can pull the n down the front using the log laws, and then I can say log of n factorial is big O n log n. Now, note that if we've got two functions f and g, f1 and f2, and f1 is big O g1 and f2 is big O g2, then the product of these two is big O the product of these. And that's a useful fact there. Also note that if we've got a constant, if c is a constant, then c is, we can write as big O of 1. Okay, because c divided by 1 is less than c plus 1, say, and so therefore c is big O 1. So you can get rid of constants in that way. Just to find another example here using the ideas here. So for example, if I've got this expression here and I want to know what is the dominant term, what's the most important, what's the growth rate of this, then this is big O x squared. We can see that because well, certainly this divided by x squared is bounded for all x sufficiently large, and if I look at log of x squared plus 1, then this is less than 2 log x, which is big O log x, and so x log x is big O of x squared, because log x is less than x. So I could actually here say x log x is less or equal to x squared for sufficiently large x, and so this thing is less than big O x squared, and so the whole expression is big O x squared. So just a couple of examples just to play with this. Now, in dealing with the sum, so in dealing with sums of this form, when we're looking at this sum here, k less or equal to x f of k, we want to be able to get some way of evaluating or getting some idea of the size of this thing, and so we're going to use the following very important result. Now remember that summation is difficult, but integration is easier, and so we're going to use the following result, which is a very important one, and it says that if this is our theorem 3.11, it says that you've got f. Now the key points here is f has to be positive and decreasing. So if f is positive and decreasing, and I suppose we need integrable, but then there is a constant k such that the sum n less or equal to x of f of n, this sum that we're of these sorts of sums that we're looking for, is equal to the integral from 1 to x f of t dt plus some constant plus big O f of x. So we can replace this sum with an integral plus a constant, and we can bury everything else under big O f of x. Now the proof of it's a little bit fiddly, but it works something like this. So I'm going to draw this, here's my function f of x, it's positive and decreasing, and the sum we're looking at then is going to be just the areas of the under the curve. There are the areas of these rectangles that I draw underneath, and I'm going to also just pick one value n and n plus 1 to look at the particular rectangle here. So firstly, on this interval n to n plus 1, since f is decreasing, then f of n plus 1, well, that's going to be just the f of n plus 1 is this height, and this is 1, so f of n plus 1 is the area of this little rectangle in here. This is going to be less than the area under the curve, which is all this bit, and this is going to be less than f of n. f of n is this height times 1 gives me the top area. So I'm just comparing areas in here, which gives me this result. And I'm going to now define a sequence a sub n, which is going to be f of n minus this integral. In other words, it's this one minus this one, and that's clearly positive from what we've written here. And I can also say that this is less than, because this is bigger than that, this quantity is less than f of n minus f of n plus 1. So we note we have this sequence, we've got a bound on it, and we know that the sequence is positive. So this number an is then, of course, just the area between the curve and the big rectangle from n to n plus 1. In other words, it's this little area in here, between the curve and the dotted lines. So now, if we take any positive integers m and n, m less than n, then I can take a sum of this new sequence we've just defined, and by the way we constructed this, this is going to be less than, using this result up here, this is less than f of n minus f of n plus 1, and then f of n plus 1 minus f of n plus 2, and so on all the way down to f of n minus f of n plus 1. And this is a telescoping series, and so this is f of m minus f of n plus 1, and this is, because this is positive, this is less than f of m, since f is positive. So that tells me at this stage then that this sum from m up to capital N is non-negative, and it's bounded above by f of m. Now, in the case when m is 1, we have this sum then is less than f of 1, and that means the infinite series that we have, this infinite series sigma an going now to infinity, converges since its partial sums are bounded and the partial sums are increasing. And so by monotone convergence theorem, this has a finite limit. So let me call that infinite sum k. Then k is a constant that's determined solely by f and is independent of n. Now I can write this k then is the infinite series, so k is the sum for n equals 1 up to capital N, plus the tail of the series is the sum from capital N plus 1 to infinity. And then by this line here, by star, the sum, if I replace m with n plus 1, is less than f of n plus 1. And that means the tail of this then, the tail of the series, is big O f of n plus 1. Now, referring back to our definition of a of n, this k is the first n terms of the series plus the tail, and the tail we've shown is is big O f of n plus 1. And I can then go back and write this a sub n back as to what it was, and a sub n, remember, was the sum of this one then is the sum of the fn's minus the sum of all the integrals. So we're taking a sum of, at this point, of this one for n equals 1 up to capital N. So we can just add all those integrals together, and that gives me this expression here. And of course we've got plus big O f of n plus 1. And rearranging this gets me the sum n equals 1 to capital N of f of n is equal to this integral plus this constant k plus big O f of n plus 1. Finally, we're getting very close now. We're going to put n to be, this capital N to be the floor of x. So put capital N now to be the floor of x in that expression. I'll just leave it there so it's still visible. Put this to be the floor of x. And we can then see that this expression here just turns into this. So this is now the integral from 1 up to the floor of x plus 1 f of t dt plus k plus big O f of the floor of x plus 1. Finally, we can deduce, since f is decreasing, we have that the integral, this integral here, is less than f of x. So f of x plus 1 is non-negative and less than f of x. And finally, we can just plug all this in. So this was the integral from x to x plus 1, and now that gives me the integral from 1 to x plus the integral from x to floor of x plus 1 plus k plus big O f of x. And I can bury this one inside. This is less than f of x, so I can bury this integral in the big O notation, and I just get the integral from 1 to x f of t plus k plus big O f of x. Slightly technical proof, but very, very important fact, very important formula. It's going to give us a way now of summing these series. So, first application of this, well, we need a little lemma firstly, which we'll use to then prove our main theorem. So the lemma says that the sum, firstly, of 1 over n less or equal to x, is log of x plus gamma, which is Euler's constant, the Euler-Mascheroni constant, plus big O 1 over x. Now this follows immediately from our formula, because all I do is I integrate 1 over x, which gives me log x. I pick up we don't know quite what the constant is at the moment, and it's plus big O 1 over x. But if we take the limit as n goes to infinity of the sum n equals 1 up to capital N of 1 over n minus log n, then we know this, of course, goes to the Euler-Mascheroni constant. And so that means k, the k in the above, is just the gamma. It's just Euler's constant. Now, by the way, this now gives us a rough approximation. We can say that sigma n less or equal to x, 1 over n, we can now see is big O log x, which is what we might expect for a sum like this one. Now I'm going to state, and I'll do the proof next video, of the following important result that goes back to Dirichlet in 1838, and it says that we can find the sum of tor of n, where n less or equal to x. Now this sum turns out to be x log x plus 2 gamma, this is the Euler-Mascheroni constant again, 2 gamma minus 1 times x plus big O root x. Now that means then that the average value of this, if I now divide this by x, then I'm going to get log x plus a constant plus big O 1 over root x, and that tells me that the average value of tor then is roughly log. And I'll do the proof in the next video, but let me just show you this little picture here. We saw before that that was tor of n, so when we plot this, we see that it's all over the place. The values of tor of n shift up and down. Sometimes they'll be very large if you've got numbers with lots of factors, and then you suddenly hit a prime and it reduces down to 2 again. If you take the average value of this is the graph you get. And as you see, this is looking very much like a log. This is looking very much like log of n. Not exactly, of course, because there's little bounces all the way along it, but smoothing out the data above, we end up with this curve which is like log of x. So in the next video we'll do a proof of this, and we'll have a look and see what happens to sigma.